Okay, let's start right now. So today I'll discuss AKSZ actions and their use in mathematics. So first, let me remind that last time we came to the following form of the AKSZ action. First, I'll write mathematical formulation. This goes into, okay, I'll write it like this. T shifted by 1. T star shifted by you see something very abstract. So what does it really mean? We have y. On y, we have coordinates. And these maps are yi. On t star of y, we also have coordinates. And then call them y star. Here I have a map phi. The fullback phi of yi is a map from t shifted by 1 to sigma to Cn. What does it mean? It means that this thing belongs to differential form on sigma. Similarly, back of y I star belongs here. And people call these fields, by definition, I with the cat. And this field, I star with the cat. These y's were called A, beautiful last time, because they came as generalizations of connection. But here, I define them this way. Now, there is a symplectic form on these fields. It will be this dv form. That is an integral over sigma. And here we know why we have this strange change of parity. We want omega BV to be odd symplectic form. Now parity of omega BV equals parity of yi plus parity of yi star, and also plus dimension of sigma. And I want this thing to be equal to 1 modulo 2. That's why if dimension of sigma is even, parity is of y and y star should be opposite. If dimension of sigma is odd, they should be the same. Now, I am going to write down the action of AKSZ. Last time we started writing it down. And I propose something. Now I will write it in coordinates y and y star. It actually consists of two terms. First term is pretty simple, S1. Let me explain this term in more detail. Y with the head is some differential form. So it has components. In particular, if yi is even, what can we say about phi star of yi? It should be even. However, it's a differential form. So it is decomposed into yi, the zero component that is even, plus yi 1 form. So what is yi 1 form? If this is even, it means that this term is yi mu dx mu. I put once. If this is even, this is odd, it means that y mu 1 is odd, and so on. So this is the rule. Similarly, y star I is decomposed into y I star 0 plus y I star 1 for plus etc. Let us analyze our example from the last lecture in this format. We have 5 DAs plus what I call phi 1 DT. So this is Maxwell's field. And gauge fixing was star A equals 0 and B star phi 1 equals the gauge fixing. Let us try to analyze Maxwell field from this point of view. What does it mean? It's interesting to see what is the field phi, what is the field yi. It is this one. So yi is what? So y is actually the algebra difference in penalty by 1. That's why it's odd. And C's are coordinates. There, here. Now, let us try to analyze components of the field. yi1 is a mu dx. So totally this thing is odd. This is odd. That's why a mu, being a gauge field, is even. Okay? Now, what about field phi? yi star is, so here we have this rule. Dimension of sigma is 2, two-dimensional field. So parity should be opposite. That's why phi I star is even. Component 0 is pi. It's 0. This component 1 is what we call phi 1. So this is equation. This is via 1 mu dxu. So this is what, that's why this is. And we remember that this phi 1 actually came from the big ghost. So it's actually odd. So I spent some time showing to you how parity match. Any questions here with this games with parity? So this is the story about the action S1. And actually, the symmetry on any field that we study, so that is the big bracket, is acting as follows. It takes S of yi, and this is interesting. Is Gyi. How did I derive this? I use BV bracket to see that y and y bar are conjugate to each other. So that's why S transformation of y is delta S over delta y bar I took variational derivative here, and I got this formula. Now, do I know this formula? Of course, I know this formula, because this formula says that f of y, let me take first component. First component, that is s of a, it's a symmetry. Is d y zeroth component is dc. So this is standard BRST transformation. It takes A to C. But if I would apply this symmetry, so if I would apply this symmetry to other fields, to this field, I will get something new that is not in the BRST language. So in this sense, BRST language is deduced from the BV language. They are not equivalent, as people often say in the literature. So I explained the first term, that is relatively easy. I explained that there was nothing terrible in this term. It's not complicated. there the second term. And now let us see what I have here. I have a function So now there are several cases. In the first case, and this is the easiest case that we will consider today, where dimension of sigma is even. And today we will talk only about this case. In this case, we actually have T star shifted by 1 of y. So these objects are polyvectors. Okay, I'll keep it one. We may find out. When S1 plus S2 solve classical macroequation. First, it is easy to check that S1 is 0. Why? It is because S1 takes y into dy, and then again takes y into dy. And this is 0 because d squared equals to 0. So argument is like this. S applied to some field phi is actually S applied to phi, and here we have again S applied to phi, and this is S applied to phi. This is where applied to phi. Now, what about S1, S2? S1 applied to F of these guys does the following. It turns each field into the RAM differential. It is T total F. And now there are two important cases. Case one. Sigma has no boundary. Then this term vanishes. Case two. Sigma has a boundary. In this case, we need to take care. Actually, this argument also works here. When we study action of S on Y, we sometimes integrate by parts. So actually the formula is S1. No, okay. It's okay. Okay. And now we need to study. So now I will write this. Now let me study S2. So home assignment. Home assignment. Check. Now this is BV bracket. F with F. And home assignment 2 with the star. Check what happens if the dimension of sigma is 4. In this case, it's not a polyvector anymore. So what's going on? So, but in simplest case, it is a BV bracket. Now let us come to our example. Again. We had an example. 5d8 plus pi a squared plus t. I'll put structure constants explicit. It's not the end of the story. There was also pi tilde 1 ECA, so we recall this term. And we had also a term from the gate fiction. And I'm not sure about the sign. So, how did we got that big there? We have f being equal to now I write it in this form. Everything with the now, when I take 1/4 out of here, I am getting the first term. And when I'm taking 1/4 from here and 0/4, I'm getting A and C. So that's how it works. Then some people made the following observation. We consider the target plane as a T star shifted to 1 to G, to the LG. But this is the same as, sorry, this is shifted by 1, and this is shifted by 1 to this. Okay, so this shift by 1 is because field C is off. And here I have shift by 1, or shift by 1. And I get even shift. Even 5. Or but then people came with the following idea. Why we are doing it this way? We can try to do it in an opposite way. So what would be the opposite way? Opposite way would be to say that we have co-algebra G star that is even. And here G star shifted by 1. So even phi would be coordinates on the co-algebra, and these odd c's would be odd coordinates on the cotangent bundle tree. Good idea. So I will rewrite everything then in terms of phi. So index is down, here index is up, it is even, it is odd. I'll put heads. Now, what would happen to the term that was previously phi with the head A bar with the structure? How I would interpret it now? So I understand that these phi's are these coordinates on the co-algebra. But what happens with these a's? They're a component of the field phi star. So I will interpret it as f a. I'm just rewriting the same formula. Same formulas, but with the new viewpoint. Is it clear? I am rewriting it as follows. And this term that was very familiar from the gauge theory point of view now is nothing but a bivector. So the same model has a different interpretation. This bivector on co-algebra linear coordinate is called Kirillov bivector. And it is clear, since I am not even doing field transformations, I'm doing field redefinitions. Kirillov's bivector is Poissonian. And it follows from the Jacobi identity on this end. Okay, so at the moment, what I did? At the moment I did a reinterpretation of two-dimensional Young Mills with with zero coupling constant as a model where I have this standard piece and Kirillov bivector. But then the next step would be to say, okay, let us generalize this model and let us consider general Poissonian bivector. And this is called Poissonian sigma model. And of course, this Poissonian sigma model is of AKSZ type. Okay, so we got the sigma model. But what is it good for? So the goal is not just to find different models, but to use them somehow. And then Maxim Kontsevich found how to use Poissonian sigma model. I'm thinking, where should I write? There was an old problem of deformation quantization. It was formulated in the following way. Start with the commutative associative algebra. Deform it into associative algebra not necessarily commutative. And let us do it for polynomials. There was a theorem that I will give as a homozygote. shows that infinitesimally multiplication of P1, P2 should go to P1, P2 plus epsilon Ij di P1 dj P2 plus epsilon squared length that we don't know at the moment, and associativity implies so that they are Poissonian. So this is a statement from classical mechanics. So I want you to, so it is a third home assignment. Last time I gave only one home assignment. This time 3 home assignments. Yes.
Here there is some bracket called BV. But some
Yes,
bracket.
it is the same bracket. BV bracket, Lie bracket, Poisson bracket is the same bracket.
There's still the S2 bracket is FFBV bracket. So
Yes.
on both sides there is same.
Yes, but here is S2 bracket. Ah. I'm sorry.
Ah.
Thank you. So now Kontsevich got a great idea. And here, so the people were looking for these terms. And nobody got a regular procedure how to get these terms. And they could not be constructed in any canonical way. So Kontsevich had the following idea. So do I have time to explain it before the break? No. It's time for the break. So after the break, I'll explain Kontsevich's idea and what can be done here. And we start, as always, at 16:0, at 16:30. So it happens that we always start after the break at 4:30.
我这也是，我感觉布置那个题，我在正好就留了得10好几个，7好几道这样很慢。
我已经都打了，我有一套完整打，但是我还没切克，它有没有什么问题？我都自己先删一
留了好多呀。
就是每次我会给你们三个问题，然后3个问题你们会分3个问题，这样子。
是，但我感觉现在已经累积好多功课在没做。
我等会儿就给你们发一个。
啊，
因为我已经都打下来了，但是
我知道，但是我只是觉得是不是有点太多了？
哦，你是想让我给你做一下删减？
也不是删减，我是后期一下。
可以把我是想着把某些特别难算的当做bonus，对，你可以做。 可以做一个补充。第一次作业我都还没改。当时我在做好作业，然后是他说有3个人，不是3次。
我就3个。
丢啊！
有3个。
我懂你的。
但是我们作业是没有那么严。
我是感叹一下，我并不反对写作业，我觉得写作业写点东西挺好的。我是觉得好像已经积累太多没写的。
其实没有的，因为它前面有标题是它不是生病了上，然后生病的前后那几次好像都没有，前面几次都没有。
我问你个特别傻的问题，就他说很简单，那个 SE bracket， 就这是第一 bracket，SE 是这啥意思啊？这 SE fine 是什么？
是
靠那括号标错，它写是 S，
它其实也是跟 fine 做不然对不然，因为
它好像是对 fine 做2次，
第一
对 fine 做2次 bracket。
哦，
它定义了一个 x， 它是用在 fine 上，就等于
就在那块括号标错的，
他应该打花括号的，
就是它的花括号标错位置了。我在那看着也，
所以他这里用了一个像那个 Jacobian 的一样。
哦没有，就是单纯计算。
他这个 SEC 是零，但是
它
它是一个
写
fine
法
上。
它的写法是这样的，首先你有一个 FTX， 你可以定义另一个 x， 它是这个东西。
对。
这个
这有个 S。
就是它用的同样的符
号。
比如说我
行，
有 SP， 然后它 SP 也可以用在 fine， 它就是原来的 x fine 做
OK， 然后它这个 SE 和 fine 做 bracket 做出来是 T fine， 这是啥意思啊？为什么 SE
算出来？
那比如说这个啊，这 SE 它就是这个SE 就是很简单，看着是很简单的关系。
因为就是这个。这样啊，反过来，然后这个是第一个，第二个，你作用起来，你会发现它里面如果有
那比如说我这里来一个 SE 和 YI 好吧 ，YI 这样一个 Y， 对，他的意思是这个 S 这个玩意儿，对这个 star。
对 x， 但是因为你的后面那个 y 判 x 上，这一项，你这也是，然后有 yi， 这里有 y star， 所以，
那我想再来一个，这是
又没有后面这个前面有 y， 然后也可以做一个这个。我也是这样来想的事情，它就这个样子。
帅。然后它 SESR 这一通就是说。
一个 B bracket 加运算嘛，第一个是在运算，然后这个 DUI star 是让 x DUI， 这个是可以导出来的运算价值刚好。所以以 general 来说，你的 x 最后在某上都是点 D。
然后这样做，算完这一通想干什么？为什么算这些 SESR
这个然后它后面举了个例子，什么情况下 f 这个算起来是正向，然后 f 长这样，然后长这样的时候，你可以对它换一个解释，这个意思，换一下，它啊，对，接着来算 f 是这个意思， 逻辑是它计算器的，可以像它的形式。
他可能说这个有用，就是说
这个东西不是解释那个两倍式，2D 两倍式，这是2D 两倍式还是？
就是说，如果是这个 director 是这个样子，就是2D 两倍的模型。然后再搞一般跟一般的 director 在这儿放。但是一般的 director 可能在 quantization 也会有 definition 里面会有解释。
对，
为什么需要有一个 persona？
就是有那些出现的一些，它是把你的 product 就是你的 product 可能会是很多的定义成这个样子，然后你还要求这个 product 是谁去带进去，给你带进去。这个是
他想解释，就是这个式子，他想考虑一个一般的parameter，但是还不能太一般，就像把这个 persona 就是它 brackets 的自己写，然后这个条件自然会在这里面出现，对不对？所以他这里想解释的是什么？
来学校就是做一个 bracket， 就是做那个 classical， 所以算那个它的一个标准。
不是那个啥问题，是这里面有题。我感觉这个做基本可能还 make sense， 有个题在这里。这都是啥玩意儿？有个题在这里。
有 five
啊，这个题只是一个 drum
differential，
跟
sigma 上的 drum，
这其实都是 differential，
也都是也不是 sigma AKSZ。
对，那我再问一个啥问题？啥问题？这个地方有一个 coordinate 是这里有一个 x， 然后你说这里有个 phi 打过来这里有个 x，q 打到这里一个，比如说是 yi star 这里的 x， 我随便说一个。然后他想说这个是一个可以看成是 pullback 这个 yi 的话是变成一个 y star 的话可以变成一个 different form， 对 signal， 为什么？这什么意思？就这里有一个，比如说这里有一个。
它实际上你的 yi star 是什么？你 pullback 之后，它是 P1 sigma 到 C 的一个函数。这个东西是这个东西就是这个东西，这个 space 是这个 space， 这个上面也有关于的 x even odd 差，它这个东西就讲开来写的。只有一些就是让 x 在这样形式，所以它就是相当于就是，所以它是这个不用管它，不用管这个 phi 句式，你只需要知道它长这个样子。
对，我还想提醒一点，这个 yi star， 所以是一个是长什么样的
y
我承认你这个可能像是一个 form，
对，
但是这个 y star 在你这个形式
y star， 你没有 pullback 之前，
对，
它是个 coordinate，
没有 pullback 之前这个 y star，
有 y，
那如果我想 pullback 以后是长这样，是 fx 3这样，那我 y 我 pullback 是这个，那我没 pullback 是啥？
那你在这个上面的 correlation 来做，你是想把它写成 x 的形式 ，x 形式那就是覆盖后，
就是你意思是这整个就是 y star，y
star 覆盖后，
对，这整个就是 y star 覆盖后，
就是你的参考，那个其实应该是这是个 y 是，
就是 y star 就等于这个。就是
不，你注意了，首先接头来看，你有一个这样的 map， x 到 y， 然后你上面有个 coordinate yi 到 C， 然后单说 yi 只有这部分，然后有 yi 来做， 是这个部分，它实际上是 y 来布置的。这个就是 y 知道，就它的一对，然后不要去想 y 来，就不要看，不要看，就看它就是 y 上的一个固定，y 上的概括，还有 local 固定在它有某一个是非常。
比如说我这个，如果后来是3这个，那我这个里面长什么样子？就比如说我现在这个叫 y， 我如果这个
这个是 y 还
对 y 还是
那你在公司有做有算法，有把这个代码，然后给你知道快的形式怎么做。
So, idea of Kancelich was the following. Okay, now I write this one. Find these dot terms as correlators in Poissonian sigma model. At first, the idea was the following. If we take Poissonian sigma model and consider correlator of observables associated to functions, then most probably product that we will get would be commutative and associative. Just imagine that we can move a point because this is a point x. Dx of O F2 is f of something. We already have seen that in Poissonian sigma models V appears as a result of the action of S on fields. It's okay, but in this way we could move points freely on the sphere, and we will not get non-commutativity. So sphere is not what we actually want. So what else could we use if not a sphere? So he had a great idea that instead of the sphere, we should use this. Now, it would be nice to put observables associated to the functions on the boundary of the disk. They could move along the disk, keeping their order, but they could not jump one above another. So how to get disk in this business? There are several steps. I would like to consider this as a perturbation. Really, we are looking for the theory perturbative in pi. So it's good to consider it as a perturbation. So if we consider this as a perturbation, then we are left with quadratic field. Where we know how to compute correlators. Deal it's exactly for you. But we need to do a gauge fixing. So what kind of gauge fixing we would like to do? We would like to do the same gauge fixing as we already studied. If we put this gauge fixing, then this action would be non-degenerate. Okay. So this is gauge fixing. What else should we do? We need to impose boundary conditions. We need such boundary conditions that the boundary terms of the action should vanish. So what are the boundary terms of the action? So this is restricted to the boundary. So how make it vanish? The easiest way to make it vanish is by star restricted to the boundary vanish. Actually, both terms vanish. Okay. So we have found. Now we are in the nice position because observables there were just functions of phi and phi star restricted to the boundary are just functions of phi because phi star vanish at the boundary. So, final procedure is just to compute correlators. How are we doing it? So now I'll erase this part of it. In quadratic theory, there is a zero phi equals to phi. So we would expand phi in the sum of the zero mode plus psi. Now let us start to compute simplest correlation. Oh, maybe it's not the right way to do it. Maybe there is a better way to do it. So instead of fixing the zero mode, we will do the following. We will take a point at infinity and say that phi at the point equal to infinity equals infinity. We will do it this. It is another way to fix the zero. Let us compute simplest correlator, F1, F2, where F1, F2 are below. F1, F2 are below. So we expand them Fi of phi would be the phi of phi 0 plus psi df over d phi I plus etc. But these psi have nothing to correlate with. So that's why this correlator equals phi 1, phi 2, that's phi 0. So it actually computes what we wanted, the zeros order term. Now let us compute the first order term. The first order term comes if we expand this phi from the action. So we put this phi here, it comes from the action, and it has fields phi star, phi star. Now fields phi I star, phi j star have propagators with the fields sides. So here I have now F1 of phi 0 plus F1 plus dj F1 phi 0 times psi j. And the same here. F2 at phi 0 plus dl F2 at phi 0 right L. Now I have fields sides, one side sitting here, another side sitting here. And I draw two green functions. So these are green functions of the operator G is a green function. Roughly speaking, this star over the Laplacian. But it happened at the point B. And then I need to integrate it over B to B. Wow, I erased this step. And as a result, I will get the correlator phi aj di f1 j f2 at phi 0, everything at phi 0 times some numbers. And this is the correct first order term. But my goal is not to compute the first order term. My goal is to compute higher order terms. How to compute higher order terms? In order to compute higher order terms, I expand the interaction term many times. And I draw all possible lines. Like this one, and like this. Each arrow corresponds to green function. And I have to integrate, so in this case, to d to the power 3. D to the 1, d to the 2, d to the 3. And in this way, I'm getting a solution to the deformation quantization problem. So it is a Kontsevich solution. Now I need to tell you where Poissonian condition on bivector comes. It deserves some time, and I will spend this time. Very sorry. Hello? Hello? Yes? So, sorry, what happened? Okay, so I am at work, and when I'll be home, I'll be back. Окей. Привет. Что случилось?
Это женщина, которая с тобой говорила. Я была в машине, а я ехала и там машина, она остановилась, и машина очень классная. Девушка ее очень и она меня врезала. Я упала с велосипеда.
Ты цела?
Я
Это не страшно. Чем ударить? Это не страшно. Да?
она сказала, что она хочет что ее точно не
Ну, конечно, бывает, прости, и нет, никакой, скажи, что со мной поговорила, всякое бывает, это самое, пожелать здоровья, чтобы дочка не попадала в машину. Скажи, что со мной так поговорила. Если нужно, я сам могу поговорить. Hello. So we discussed the situation. Everything okay. Everything is okay. So just let your daughter to take care of herself, because would it be more serious evil? She could be injured. It is nothing. It is nothing, nothing secret. We discussed it with my daughter already. So, okay, so please. Yes, so you see, it's just small accidents, things happen. So just take care and relax. No, I think she could easily. So you may ask her, but I think that she would prefer to write home by herself. Yes, but I discussed there is not real problem. Things happen, you know. So it's, okay, so when she will come home, okay, so we will take care of her. So it's not an object. Okay. Да. Ну, сможешь сама доехать до дома? Или нужно на машине? Скажи, как тебе комфортнее? Скажи, как тебе комфортнее? Хорошо. Пока.
Excuse me.
Yes.
Before you explain Bosonian steps, may I ask what's the integrant you need to integrate so we get the correlator?
So here we have points. Sigma 1, sigma 2. Here we have real functions from the integral disk. Real function z sigma 1. And for this problem, we integrate to z over the disk.
What's the role of this casino? Why?
The field psi have correlators with field phi star.
Yes.
So field phi, phi naught, that is a clone. Left side. There is a correlator psi phi star. That is a green function. Sigma. So when I decompose functions of the field phi, I have function of field phi naught plus derivatives times field psi plus probably more derivatives, but in this simplest case, one derivative is enough.
So, do we have a definition of this correlator? Because using green functions like a technique to calculate this correlator.
So the definition of this correlator is a Green's function.
By using green function to define.
So G sigma z is an integral kernel of B star over notation. So there is such an operator, it has an integral kernel, green function is an integral kernel. So we put here the green functions.
In higher term case, there are multiple ways to connect such.
Yes, so we need to sum. Sum over all ways.
So
To connect.
the summation is in the definition of the operator.
Yes, of course, because it is this summation over all ways is called big theory. From one to two. That if you have some number of fields of one type and fields of another type, you may call possible contractions. It is a big thing. But that's how the structure is obtained.
So when we define such thing as operator, then all higher terms will give us a structure which
appears in
solve
information.
the,
Yes. And now let me try to explain why it happens. So I need to explain two things. First of all, why it happens. And second, where in construction condition of pi being Poissonian appears. So I need to explain two things. And I'll explain these two things in one construction. Let me consider the disk with n points on the boundary. And k points inside. There is the configuration space that I called conf and k. That is so how should I explain it? So here, so I would like to consider this configuration space. So space of coordinates. Of corresponding points, modular, that's important. The following group, S, L, U, R. Now, what is the meaning of this SL to R? You may consider this SL to R as a group of isometries of Poincare disk. However, the deeper explanation of this SL to R is the following. If we have CP1, then it has holomorphic symmetries that form group SL2T. If I have CP1 with an equator, the group that preserves equator is broken to SL2R. Let me consider the sum of the products of green functions that I symbolically write like this. It is a differential form on quality. Second, it is closed. So it is a differential form because fields that stand here and stand here are differential forms. In particular, here on the boundary, I can have not only a zero form, but also one form. Remember that on the boundary I have phi hat, and that is phi 0 plus phi 1. So it's actually a differential form. So it is closed. Property number 3. It is factorized. So factorizability is the fundamental property of quantum field theory. I will not prove it. In the mathematical paper of Kontsevich it was proven. But factorizability means the following. So I would like to see what should I arrange. When several points on the boundary and the bulk come together, it is better to consider them as follows. So it's better to explain it in pictures. No. Suppose I have a disk. And suppose here 3 points on the boundary and 2 points on the bulk simultaneously come together. And there are other points somewhere. Okay? Then what happens with the correlation function? Correlation function looks as if, in this particular example, either the following happens. So these points leave outside. However, this small group of points goes on the bubble disk. So correlator behaves as follows. And this property is called factorization. Where a group of observables come together, it's just like a piece of the space-time decouples. It's called, and then correlator becomes a product of this correlator times this. It's called factorization. So now I would like to combine closedness and factorizability together to get associativity. The following space. Any number of internal points, 3 points here and 1 point where I have delta function. Not the 2, as I studied before, but 3. 3 is not 2. They're different. It's not a misspell. And this space has the following boundary. It has a boundary when 2 goes to point number 1. It's one boundary component. It has a boundary when 2 goes to point number 3. And it also has very specific boundary components. When 2 points in the bulk come close to each other. 1 point in the bulk comes close to the second and rotates around. Let me call this boundary component 0. And then, since differential form is closed, its integral over the boundary is 0. So integral of the correlation over the boundary equals to 0. But now let us see what kind of components do we have. Due to factorizability, it is 1 times 2, and any number of internal points, plus, or actually a sign here is minus. Minus, here is 3, minus 1, here we have 2, 3, plus contribution of equals to 0. Now, what is contribution of? It is easy to compute using what people call operator product expansion. Dima, it's for you. So correlator between these 2 points is a green function and integral over the green function over the circle. And it is exactly the boundary contribution equals to 1. So if there is a green function between these 2 points, then we have this contribution 0. So we need to collect all green functions that happen here. But how they happen? We have phi star at one point. We also have phi star at another point. So to get green function, we need to extract psi from here and phi star from here. But this extraction is exactly the bracket between phi and phi. Here we have this green function. So in this way, Poissonian condition comes as elimination of this boundary. That's how Kontsevich constructed the formation quantization. And then we conclude it by the story about what I call anomaly in the formation quantization. The action is already erased. So in the formation quantization, we construct F1 star F2 that depends on pi, that goes as F1 times F2 plus higher term, inevitable higher term. Simplest case is so-called Moyer product. For the Moyer product, Ij is constant. And being constant solves Poissonian equation. And Moyer formula is known dxi dyj f of x, f1 of x, f2 of y. So we differentiate, and then we take y equal to. Very explicit formula. This formula we actually obtained from as a particular case of Kontsevich information quantization. It is because integral over positions of these points decouple. Integral is just d to c over this to the power n. No interactions between these. No interactions because the bivector is constant. Okay. Now interesting phenomenon.
Actually, before we reach this part, sorry. The correlator, the definition of correlator has already included the integration over configuration space.
Yes, but I'm trying. No, so we first compute correlator and then we integrate.
So correlator is like you fit
Correlator is-
all the insertion points.
Yes, and then to get the result, I integrate correlator. When people used to speak about correlator, they fix insertion point. So now I'll tell about interesting phenomena. This interesting phenomena is the following. The action. So put it in ID and put it consider action. We may ask ourselves, what is the symmetry of the action? Symmetry of the action is, of course, phi I goes to phi I plus epsilon di phi, where this is platonic. Because Poissonian vector field preserve phi. Okay. Well, these are obvious symmetries of the action. And of course, you want to ask what is the symmetry of this? It is the conjugate symmetry. So these are obvious symmetry of the action. You may check. Classical symmetry. But then it's interesting to see that these symmetries are not symmetries of the star product. Classical symmetries are not symmetries of the star product, even in Moyer. Let us see what are the symmetries of star product. Okay. Since star product is associated, symmetry of star product is F going to F plus star commutator F with H. This is a symmetry of any associative algebra, where H is a function. What can we say about this? H star commutator. It actually goes as F plus. You may compute it to get LVH F plus tiny pairs. So what is VH? VH is dH over d phi I phi ij. So actual product, actual symmetry of star product is not the classical symmetry of star product. And when the quantum symmetry of the system is not the classical symmetry of the system, people say that we are dealing with anomaly. The explanation of this anomaly is the following. We need to define symmetry on the quantum level. There is a current that generates this symmetry. And this current is so it is also a superfield. This current is also a superfield, so it has many components, and we will take dimension 1 component, since we are looking for a curve. It has no boundary component. With phi stars, if V is Hamiltonian. That we will assume. However, interesting phenomena is that the action of this current on a function is kind of tricky. In quantum field theory textbooks, okay, now I'll go to this point. In quantum field theory textbooks, people use the following argument. There is a free theory here is interaction, and here is the current. And symmetry actually implies the correlator of integral over the small contour. And here we put current, and here we put phi. And here, in quantum theory textbook, people say that this gamma is along small contour. Around X. And interaction drop away. And only free green function contribute. However, this theory is tricky. Here is a function f. Here is a contour, gamma. Here we put a curve. And here we have vertices of interaction. So now there are many interesting diagrams of this type. We may say, okay, let us move our contour closer to the position of the point F. But we would not reach anything, because when it goes closer, new insertions would play a role. And this is conformal property. Actually, this theory is conformal, and I may actually try to consider this as a semi-cylinder. And F is infinitely far away. And moving the contour gamma is just moving arc along this semi-cylinder. And phenomena always persist. And if we compute this anomalous thing, we will reproduce exactly what is prescribed by associativity. So this was the story about currents and anomaly, and it's the end of today's lecture.
So you mean these bulk insertions will not disappear when you shift?
So when I shift contour, one bulk insertions would not give contribution, but another would give. So this will go like this. So maybe on this picture is better. Only bulk insertions at the scale similar to the scale of the arc contribute. Bulk insertions that are far away or very close do not contribute. So when I'm coming here, these insertions will contribute. So it doesn't matter how close I would move, there will be always bulk insertions that would contribute. And that's why I will never get classical symmetry. In this way, it is a quantum field theory phenomenon. The symmetry is defined not by the change of variables in the action. In some cases, one should be very careful and define symmetry on the quantum level. So that's why when Kontsevich made this paper, he first wrote to his friend that I found the solution to the problem of deformation quantization in terms of functional integral. But when he published the paper, he instead presented it as a summation over correlation functions, because this is mathematically correct definition. And if you just do hand-waving manipulation with functional integral, like I did, just do transformation of fields in the functional integral, you could be in trouble. And cases where you are in trouble are called anomalies.
I want to ask, classical symmetry is not a quantum symmetry.
Yes, classical symmetry. This is classical symmetry.
Just higher terms disappear, it's still not a quantum symmetry.
So without this, it is a classical symmetry. It's the symmetry of the classical action. But actual symmetry of correlators includes these higher terms. So the question how these higher terms appear. They appear from bulk insertions. And there is no way to get rid of these bulk insertions, even by moving the quantum.
Sorry, I don't quite understand. You have, for example, here you have 3 bulk insertions in this example. But
If I have 3 bulk insertions, I can get rid of all of them moving contour here. But in the correlator, I'm integrating over position of the bulk insertion.
I see.
So in this term, I see the origin. When I'm doing formal manipulation with functional integral, I don't see what's going on. That's why formal manipulations with functional integral are dangerous. And all mathematicians know it. That when you are doing formal manipulation with functional integral, you could be in trouble. And you should always make a check. That formal manipulation gives you exactly what actually happens. And every time you are not getting what you want, you should study what's going on, try to find the origin of the problem, and remember it for future.
So if it's without interaction, I mean, in a free theory.
So in textbook, people say, when you look at the symmetry, interaction is proportional to the area. So in textbook, people used to say, interaction is proportional to the area. When contour shrinks, you may drop it. In conformal field theory, you may not drop it, because its theory is conformal, and there is no such concept as small area. So interesting phenomena could happen. Okay. See, we have no problem. I will relax in my office.